You see it?
Yes, it's clear. Yeah, you can continue.
All right, thank you. Professor Dinda, thank you very much for your kind introduction. And good morning, everyone. Probably it's in the morning in India, right? So,
Yes, it's the morning.
okay,
Right now 11:15.
okay, thank you very much. I'm very happy to have a talk today in front of the many people. So as shown here today, I would like to talk about the modern inclusion control technologies for clean steel production. So it's already introduced by Professor Dinda, but I uh, put my self-introduction first, just slightly, and then I will follow these contents. So first of all, my short CV, it's already explained by Professor Dinda. I got the PhD in the University of Tokyo in 2006, and then I'm mostly working on the chemical metallurgy part, mainly focusing on the steelmaking process. So currently, I'm associate professor in the Department of Materials Engineering. So uh, I just summarized my current research topics in this slide. So I'm mostly focusing on iron making and steel making side from the iron ore sintering process to the casting and as well as a little bit about the heat treatment process, a part of physical metallurgy. But I'm mostly working on the chemical metallurgy part after the blast furnace, before casting. So anyway, today my research talk is focusing on these parts, mostly the control of inclusions to produce the high quality steel products. Then probably most of you may have already studied those things, but firstly I want to talk about a little bit background of how the clean steel is produced and how the clean steel should be produced. So as you know, the high quality steel uh, needs some important points like these, like reliability of the materials. So no destructive or severe damage must be made by the steel products. And then this would promise a long material or product life. The high performance of the product can be achieved by high quality steel, and it will result in the lower environmental load of the product and also the long material or product life. And then if you can achieve the very high quality steel, you can you might be possible to achieve some new functions. And then it will uh, be continue to the development of innovative application of steel products. So anyway, I can say that the high quality steels can be made from the clean steel, and actually the production of clean steel can be explained from the following viewpoints, such as lower impurity concentrations of the steel materials, or the less defects during the solidification, or the the post casting physical metallurgy part, or the some clean steels with less non-metallic inclusions is important. And then today I want to mainly focus on the lower impurity concentrations or the less non-metallic inclusions steels. So this is just an example how the clean steel is important for life. So here just there are some beautiful figures of automobiles. And then actually this kind of automobiles are produced from the steel coils, steel sheets like this. And then we have many processes like forging, welding, painting, assembling, and so on. And then finally, the beautiful automobiles are produced. But as you know, actually, this, for example, this automobile cannot be made from the one steel coils. Actually, this kind of automobiles are produced by combining so many kinds of steel products. This figure shows the relationship between the tensile strength and the total elongation of various steel products for automobile steels. As you know, from the very soft material like interstitial free steel to the martensitic steel, very hard steel materials. And then we need to actually combine these various steels from the soft to the very hard materials to make the one automobile, which is quite safe for us, as well as to produce a very beautiful uh, outview, the outlook of the steel automobile. And then, in order to achieve these properties, or in order to control flexibly produce these steel grades, we need to control the microstructures, or we need to produce these with no defects, and also we need to produce the steels with proper alloy designs. Then, if we can freely select these steel products, we can use to assemble the one automobile like this. Sorry, this is in Japanese, but it shows the tensile strength of the steel materials. Actually, one automobile is made by combining so many kinds of steel products. Uh, for example, when we only see the tensile strength of the steel materials, you can find from the very soft materials to the very high material, and many parts are produced from many types of steels. Then, actually, the properties required for automobile sheet steels are summarized like this, for example. For example, of course, sometimes we need a higher tensile strength, but of course, on the other hand, we need sometimes the very soft materials. Uh, Sometimes we need a better machinability of the materials, better welding properties, better coating or painting properties, and also sometimes the better shock absorption properties are required. This left bottom figure shows just a comparison of the shock absorption properties of the conventional steels and the newly developed steel product, which is taken steelmaker's website. So anyway, when you provide the same load to the steel materials, you can see that the deformability of steel materials greatly depends on the property of material. And then, actually, some part of the automobile is necessary to absorb the shock energy. The collision energy, for example. But some part of the automobile is necessary to keep its shape in order to keep the people safe inside this automobile. And also, if you consider to buy a new car, of course, the very beautiful car is welcome. And then better surface beautiness is required, which means that we hate any slivers on the steel materials. For example, if the steel sheets have slivers more than 20 micrometers in width, are not acceptable in the Japanese automobile companies. And these kinds of slivers are mainly produced by the non-metallic inclusions contained in the steel slabs. And that's why we need to eliminate the inclusions as much as possible. So, okay, so just I introduce the background, why we need clean steel, and then I want to talk about the non-metallic inclusions. So actually, I'm not so sure which grade of students are joining in this talk. So I want to just talk some introductory part of the non-metallic inclusions. So the non-metallic inclusions, which is simply always called as inclusions, is a non-metallic phases besides the main ferrous phase. So such as oxide, sulfide, nitrogen, blah, blah, blah. This right figure shows the SEM image of the oxide inclusions in the aluminum and titanium alloy steels. So this is not a commercial product, but actually this is the samples prepared in my group. So that's why this sample is quite dirty and contains lots of inclusions. So you can see the very tiny inclusions as well as the very relatively large inclusions like this. So when we see why the inclusions are produced, you can see the source of inclusions like the entrapment of slags, refractories, and so on during the refining process. Or sometimes the reoxidation of molten steel is experienced, and then the easily oxidizing alloying elements are oxidized to change to the non-metallic oxide inclusions. Thirdly, the remaining product of the deoxidation reactions becomes inclusions like this. So I will talk the deoxidation later on, but anyway, this is some reaction to remove the soluble oxygen in molten steels as much as possible. And lastly, of course, the molten steel will experience the casting process to make some shape, and then the temperature drop or phase transformation of steel will cause the oversaturation of solutes, and then the precipitation of oxide, any inclusions happen. So actually, these are the main sources of inclusion formation. And then, as I mentioned a little bit, the problems induced by inclusions are summarized here. First part is the critical influence on the steel properties. So like elongation, corrosion resistance, and so on of steel products. So if you have some, some inclusions in the steel materials, actually the shear stress is concentrated uh, on the interface between the non-metallic inclusions and this matrix metal phase. And then the cracking will be initiated from this point. When these oxide inclusions are exposed on the surface of steel products, actually the corrosion will often happens from that point because of the different electrochemical potential of the material. So this is one part, the deterioration of properties of steel. The other one is the many troubles during the refining operations, such as clogging of a submerged entry nozzle, which is installed in the casting process. So when you pour the molten steel to the caster, you need nozzles. But actually, those kind of oxide inclusions accumulates on the surface of inner wall of the SEN, and then the SEN becomes, the inner diameter becomes smaller, and then clogging happens. In that case, you need to terminate the operation, and then you need to change the SEM, which will reduce the productivity of the plant. So from both viewpoints, we need to eliminate the inclusions as much as possible. So, firstly, why the inclusions are very difficult to escape to form. So actually, this figure shows the oxygen concentration at the end of the converter process. So in this figure, you can just see the two cases using the LD converter or the bottom blowing converter. Anyway, this figure shows a relation between the carbon content and the oxygen content. So as you know, the converter process will will decrease the carbon concentration. And then in order to achieve that, you need to uh, uh, use oxygen gas. But so you can burn the carbon, but instead the oxygen content in molten steel inevitably increase like this. So at the end of the converter process, the oxygen content in molten steel would reach to several hundred ppm. That is the source of the oxygen in molten steel. This is the another case, and you can see the change of the nitrogen content during the refining process. So I don't talk the left side figure, but you can see that the nitrogen content in molten steel will vary like this through the refining process. So in the hot metal, normally the nitrogen content is around 50 ppm. And then during the converter blowing process, the nitrogen is also removed somehow. But after the tapping, the nitrogen is again absorbed from the circumstance air, and then the nitrogen content increases like this. So if you do not remove these dissolved nitrogen until the end of the casting process, the nitride would precipitate due to the temperature lowering and then the oversaturation of the many nitride compounds. I will skip this part, so I already discussed this one. Other bad point when you have inclusions in the steel products are just summarized here. Those are just the example, but the first one is the case, the production process of drinking cans. Nowadays, it's not so easy to see the drinking steel cans in Japan, but we still have some products like, I mean, the can material with foods or something. And then anyway, those steel cans are produced from uh, I mean, the plate making and also the uh, drawing process. So you need a deep drawing actually when you want to produce a two pieces can, which is composed of the body with a bottom lid with a separate top lid. And then in that case, you need to draw the steel plates very deeply. But if you have any tiny non-metallic inclusions, the breakage of steel sheets happens from that point. And then in that case, you need to suspend the can production line, and it will lower the productivity of the process. So actually, the steel in this is Japanese case, but steel quality demanded from the can producer is to realize the less than one can per 1 million cans production. I mean so if we want to 1 million cans, uh, you must avoid the even the one can fracture. So in that case, the less than 1 ppm of the fraction defective is required. This is quite severe for the steel makers. The other case is fatigue of bearing steels. As you know, the bearing steel experience a very high mechanical load, and then very cleanliness of the steels for bearing steels is required. I'm sorry, but this is written in Japanese, but this figure shows the relation between the oxygen concentration in the steel products on the horizontal axis against the reliability of the material. So you can see that the reliability of the steel materials for bearing steel will increase dramatically by reducing the oxygen concentration in steel products. And then this oxygen content is actually the total oxygen content, but uh, this total oxygen content is almost equivalent to the oxygen amount as inclusions in the product. So you need to reduce the amount of inclusions as much as possible. Right side figure just shows the one example of the accident happened in Japan. Again, sorry, this is Japanese, but this figure shows some accident happened in Japan about 14 years ago in the Shinkansen. I'm not sure you know Shinkansen or not, but this is a bullet train. And actually, the Shinkansen train runs with about 300 kilometer per hour during the operation. And then here is the gear to run the Shinkansen. And then in the original product, you can see the many bearing parts are here. But actually, after opening this part, after the accident, they could not find these bearing parts. So what happens during the accident is actually the breakage of bearing happens. So that just the bearings separated into the many pieces. And then because of the very high speed running, uh, due to the huge centrifugal force of this bearing steel parts, it broke this gearbox, and then some damage happened like this. So if you have a severe accident for the bearing steel, it will cause a huge accident like this. So in this case, there was no, the human being damage, but it was quite severe at the time. The other part is steel wire productions. For example, just for tires, you can see that the tire is composed of the rubbers with very fine steel wires. And then you need to deeply draw to produce these steel wires. But so you can see that this is a steel wire uh, with the diameter of about 300 micrometers or so. And then actually during the drawing process, when you have inclusions, something like this, the fracture of the steel materials happens from this point. And then again, you need to stop the operation. So the avoidance of inclusions is quite important. This is another case for valve spring steel. So you can understand this valve for engine is will experience repetitive load at high speed cycles. So if you have again the inclusions, actually the material life of this steel valve is reduced like this. So in order to keep the steel materials life, we need to make clean steel. This is other case for stainless steel, but I will skip this part. So I just introduced many examples how the non-metallic inclusions make a bad issues for steel products. But some studies also show the possible utilization of non-metallic inclusions. So this is just a summary of those things. First one is the control of mechanical properties. So as I already mentioned, when you have non-metallic inclusions, the mechanical strength of steel materials is reduced by some mechanism. But which it means that if you can precisely control the dispersion of inclusions in the steel materials, you can improve the machinability of steel. So, as you know, the traditional, the tool steel, machining steel, high-speed steel, for example, the lead sulfide or manganese sulfide is utilized to improve machinability. And then such a case can be applied to produce the very high-grade steel. So this is just one example. It is quite old, but this is some materials for the iron nickel alloy lead frame for, the semiconductor chip. So in that case, you need to make a very fine structure of the steel sheet, and then they try to disperse the manganese sulfide inclusions very tiny and very uniformly within the steel materials. And then you can improve the machinability and actually this, I mean the, you can very, uh, the cleanly cut the steel materials. The other case is just this is a fundamental research to see how the morphology of manganese sulfide inclusions in iron manganese sulfur steels changes with cooling conditions or the content of manganese and sulfur in steels. Oh, I'm sorry. So the other point is that it also can improve the mechanical properties, but in this case, actually, the some particular inclusions like a boron nitride or titanium nitride to improve the ductility of the weld steel materials at the heat-affected zone. So whenever you produce the huge steel products, you need to bring the large steel parts, and then you need to connect these steel materials by welding, for example. And then if you need a welding process, you need to put a quite large heat. In that case, the weld metal is molten and solidifies again. Uh, So the problem of that welding process is that actually the extra heat is extracted through the connecting steel materials, and then uh, the uh, the next part to the weld metal is significantly heated up to the before still below the melting point, but a very high temperature. And then actually the coarsening of the steel materials happens like this. And this coarsening of the grains will reduce the mechanical strength significantly. But some if you can if you can put the boron nitride or some titanium nitride in these steel materials, the tiny dispersed boron nitride or titanium nitrides can uh, prevent the austenite grain growth, and then uh, the coarsening of the grains avoided. In addition to that, the boron nitride or titanium nitride actually have the effect to promote the fine ferrite grain formation from this inclusion surface. So from such a viewpoint, some type of inclusions are quite useful, but the bad inclusions must be removed as much as possible. Then, yes. So so as you know, the influence of some basic impurities are just summarized here. So we are focusing on the sulfur, for example, because it will make the sulfide inclusions, or the oxide inclusion. So oxygen is quite important, or the nitride inclusions are important to control. So nitrogen must be controlled like this. I didn't mention there was a carbon content, but the carbon will also produce a carbide inclusions. So we need to control these impurities simultaneously to achieve the necessary properties for steels. So strategy for the impurity removal is just summarized here. So sorry, this is for the also contains phosphorus, but for the case of sulfur, you need to utilize a large capacity flux, and then you need to remove the sulfur as much as possible. And then you need to combine the various processes from the hot metal pretreatment to the primary and the secondary refining process, even the final casting process. The tarnish may have some functions to remove sulfur in steel. In the case of oxygen, carbon, or nitrogen, you need intensive degassing treatment. And then the deoxidation in the vacuum degasser is quite important. In some cases, you can use some special secondary refining process like a ESR or a VAR or other processes. Again, it depends on the steel grades you want to make. So if you want to produce a very low oxygen content, for example, less than 5 ppm oxygen content in total, you might be necessary to use some special treatment process like this, or special continuous casters, not the conventional vertical bending caster. And then this is a pretty important point, but sometimes we forget about this. For any impurities, we need to be sometimes carefully choose the alloying elements or linings and so on. For example, if we want to use the cheap ferroalloys, ferrochromium, ferrosilicon, ferromanganese, blah, 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 and in that case, you can buy a cheap one, but in that case, some impurity contents, not only carbon, but some other content like a sulfur might be high. So in that case, you need to think if you can remove the additionally coming sulfur or carbon can be removed after the alloying process or not. So if we cannot remove any particular element after that alloying process, you need to avoid. And then you need to pay some additional fee to buy the relatively excellent grade ferroalloys to avoid the contamination. Okay, so thirdly, I just shortly talk about the thermodynamics of the non-metallic inclusion controls. So as you know, the compounds dissolved in molten steel precipitate as a non-metallic inclusions when the contents exceeds its solubility. So if the contents are less than solubility product, it's okay, but when the content exceeds its solubility, this reaction happens to the right side, and then there's some compounds is formed. If this is oxide, it becomes oxide inclusions. And then from the thermodynamic viewpoint, the solubility or the standard gives energy change of this reaction is important. And then we need to understand how the thermodynamic data of these kind of reactions are quite important to analyze the process itself. So if you have some dissolution reactions of a product in molten states, you can write this equation, and then you can easily derive the equilibrium constants like this. So from the viewpoint to remove any gaseous species from these reactions, you can understand like this. Firstly, you might be possible to remove the impurities by compound formation. So when you can make some compounds like this, and then normally most of the inclusions, oxide inclusions, are lighter compared to the molten steel, and then it flows up actually. And then the decrease of oxygen content can be decreased by the oxidation reaction like this. Or the interstitial elements such as carbon or nitrogen can be achieved, can be fixed by using some alloying elements. And then in that case, the nitrogen is fixed as a form of compound. So if this is carbon, the carbide is formed. Actually, this is a way to produce interstitial free steel. So anyway, for the oxygen control or the material property control, the thermal data are also important. This is the same thing. So oxygen content control is especially important during the secondary refining process. As I mentioned, at the end of converter process, the oxygen content goes up to the several hundred ppm, and then you need to remove it basically in the secondary refining process. So normally, the most of the oxygen can be removed by using a dimming action shown in this equation. And then the carbon and oxygen in molten steel will be simultaneously removed as a form of CO gas. And then you can achieve to some oxygen concentration. But you cannot reduce the oxygen content to very low level. So the remaining oxygen after remaining actions should be removed by the oxidation process. In this process, some metals which are easily reactive with oxygen compared to steel is added. And in that case, the Ellingham diagram is quite important to see. So as you know, when you see the Ellingham diagram, here is a standard Gibbs energy change for the formation of iron oxide. So in order to remove the oxygen in molten steel efficiently, you need to add some highly active element compared to iron. So you can choose some elements from the Ellingham diagram below this red line. So the typical deoxidation metals like manganese, silicon, titanium, aluminum, blah, 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 can be seen here. And then you can easily understand that the manganese or silicon is, the middle reactive element to oxygen. If you add aluminum or magnesium, these are the very strong deoxidizer. And then depending on the steel products, you need to choose those things together. So When you see the dissolution reaction of any oxide, it's described like this. And then from this relationship, you can finally see that the oxygen content is a function of these things. Please make sure that the activity coefficient for oxygen or the oxidizers are the function of oxygen content. So this is not uniquely, I mean the this is not easily solved by adding some numbers, but actually these are the equation of against I mean the oxygen content. Then you need to solve this. So uh, when the product, I mean the oxide materials is oxide inclusion is pure oxide, you can put input this activity of some oxide is as one, as unity, and then the oxygen content equation can be converted like this. And then you can calculate the oxygen content. So in order to calculate this equation, you can find that the activity coefficients of the oxidizers and oxygen is quite is necessary to calculate. And then there are many methods to estimate the activity coefficient of solutes in molten steel. So roughly, I can say that in the plain steel, the first approximation is a dilute solution approximation. And then when this is applicable, you can introduce the interaction parameters. Sometimes the common interaction parameters are not applicable for some state grades. In that case, you need to introduce the higher order of the interaction coefficient, interaction parameters. In the case of special steels, since this is highly alloyed, you cannot mostly use the normal interaction parameters like this. So in that case, you need to utilize the various solution models. So probably you may have already studied the introduction of interaction parameters. So definition of interaction parameter is as follows. So for solutions, the base metal is iron with alloying elements like M2, M3, M4, blah, blah, blah. In that case, the activity coefficient of M2 is expanded in the series at all alloying elements is zero, which means that around pure iron, pure molten iron. And uh, you can conduct the Taylor series expansion, and also when you can neglect the higher order partial derivatives, you can finally obtain this relationship. So the gamma coefficient, activity coefficient of solute M2 is expressed as a function of the composition, contents of alloying elements like this. And then when the concentration of alloying elements is not so high, you can assume that this coefficient parameters is almost constant in the under the constant temperature. And then we define this parameter as epsilon MIMJ, and this is called as interaction parameters in mole. Then this is one of the thermal properties of the this parameter shows the influence of concentration of MJ on the activity coefficient of MI. And this is a kind of thermodynamic properties. And then you can determine some numbers for each parameter. Then when you have all parameters in numbers, you can convert this function finally to this form. Then you can find that the activity coefficient of M2 can be expressed as a function of concentrations of alloying elements as a linear function. And then actually, when you if you know the concentrations of all alloying elements, you can calculate the activity coefficient of M2. Uh, in the daily operation, we never use mole fractions. In that case, we need to introduce the mass concentration. So this is quite similar, or mostly same operations, but you need to be careful that this is in normal logarithm form. The previous one was in the natural logarithmic form. So anyway, in this equation, we define that the interaction parameters in weight by using this equation. Then finally, you can express the activity coefficient of M2 by this function. I'm sorry, I didn't change this one, but because of the definition of the activity of this in this form, this part is 0. So please erase this part, okay? The first one. So this is just a function of concentrations of alloying elements. And then you may see these relationships in the textbooks, so you may refer it later on. And then you can convert any interaction parameters to others, or you can also find the relation between epsilon and E as well. But whenever you want to use these interaction parameters to estimate the activity coefficient, you have to be very careful that the use of these interaction parameters are limited in the diluted solutions. So if you want to apply to the relatively highly alloyed materials, you need to be careful. And then, before that, you may see the many textbook in which the interaction parameters are summarized as a form of table like this. This is just one example published in Japan. And then you can use these data if these data are applicable for your system. These parameters are mostly shown as a constant. In that case, you may use these parameters at the temperature of 1600 degrees C. But some parameters are shown as a function of temperature. In that case, you can extend somehow from the liquidus temperature to the higher temperature, like 1700 degrees C. The issue is, of course, happens from this table. You can see that some interaction parameters related to carbon is very rich, but you cannot see the interaction parameters related to beryllium, for example. Of course, because the beryllium is quite, the rare elements in steel materials. So nobody has measured these parameters beforehand. Only the one exception between the oxygen and beryllium like this. So in that case, you need to estimate the interaction parameters by some method, or you need to measure it by yourself. So this is but it's a very time-consuming work. So this is quite important accumulation of our previous research result. Okay, so thermodynamics of solutes in high content in liquid steel should be introduced like this. So if the dilute solution approximate is a little bit questionable, you need to introduce some other things. First one is the higher order interaction parameters. So this is similar to the case of the previous interaction parameters introduction, but you need to introduce the second order or third order. It's quite rare, but sometimes you can see the third order. But anyway, mathematically, this is possible, just to introduce the second order parameters like this. So the definitions of interaction parameters in the second orders in mole are defined by these equations, or the second order parameters in mass concentration like this. But anyway, in this case, we always have a discussion, the meaning of, the thermodynamic meaning of these parameters. So this kind of discussion is still going on. The second solution is the utilization of various other solution models. So this is just an example. For example, the Darken's quadratic formalism can be used. This is for the ternary system containing ion with two alloying elements, not alloying, two other elements, M2 and M3. And then it is clarified that the relations between the activity coefficients of ion M2, M3 are expressed by these equations. And then actually, it is also known that these relations, the right-hand side relationships between the traditional interaction parameters and the new parameters, alphas, in this darkened quadratic formalism are expressed by these equations. So you can use the interaction parameters previously shown in the table to estimate the alpha parameters in these equations. And then those estimated alpha parameters can be utilized to estimate the curve activity coefficient at wider composition ranges. The other way is just another example using the Red-Dickster polynomial type for the binary solutions M1, M2. So this model is based on the uh, some data like this, and then you can easily see this form to express the excess QC energy of mixing in the form of these functions. And then you can find the omega parameters in these models. Actually, these omega parameters can be deduced from the conventional, previously introduced parameters for gamma standard or alpha parameters. But again, if you do not have, or if you cannot find the suitable omega parameters, you need to determine by yourself by several methods. Okay, the last one, this is just a kind of tip to control the inclusions. I already introduced the relationship between the oxygen concentration and some as a function of these things. And actually, you can see the activity of products, the deoxidation products. So if you can make the activity of deoxidation product lower, smaller, you can further lower the oxygen content. So you can change the solubility curve between the alloying element, deoxidizer, and oxygen content to the origin, toward the origin like this. Then, if you, in order to achieve this, one solution is to make the liquid inclusions instead the pure solid oxide product. And then if you can make a liquid inclusion, which means that there's a mixture of several oxides, and then you can lower the activity of the oxidation product and then lower the oxide content in molten metal. So I will show you the example later on about this. The For the kinetic part, you can see some phenomena like this. First one, how we can control the inclusion morphology in the steel. So this schematic figure just shows the morphology control suitable for utilization. So of course, it depends on your purpose, what kind of steel, inclusions you want to produce in molten steel. And then actually somehow the inclusion morphology can be also controlled. This is just one example uh, to show the relation between the local activities of oxygen as well as the metal. Here is the activity of oxygen. Here is the activity of metal. And then some resulting oxide inclusion morphology schematically drawn here. So you have a very high oxygen activity with a quite low deoxidizer activity. You can normally, uh, usually produce the spherical tiny inclusions. On the other hand, if you have a very high metal deoxidizer activity and very low oxygen activity, the inclusion becomes facetic like this, which depends on the crystal structure of the oxygen product. In the middle range, you can have some dendritic form like this. So you need to control the driving force. You need to control the oxygen content as well as the oxidizer content to make the necessary inclusion forms. And then you need to control the driving force of inclusion growth and duration of oversaturation condition or something like that. You also need to homogenize of the oversaturated circumstances by strong agitating of the molten metal. The other case, whenever the inclusion is formed from molten liquid, it requires some oversaturation to promote, I mean, to promote the nucleation and growth of the inclusions. So very old studies have shown that the homogeneous nucleation of alumina by using this kind of experimental technique. So they prepare the molten iron, then they very slowly put the molten aluminum on the top of liquid metal. In that case, the diffusion of dissolved aluminum happens from the top toward the bottom. But molten steel initially contains some oxygen, and then the nucleation of alumina happens within the molten steel. Actually, they conducted some experiments and also they quenched the sample after the experiment to see where actually the alumina inclusions are formed. With some theoretical analysis, they finally derived this equation to calculate the nucleation rate of alumina inclusions as a function of many parameters like this. But you can see that the first important thing is that eh, えーっと、sorry. Yes. So nucleation rate is also derived this equation, can be expressed by this equation. And also they studies the supersaturation degree. The supersaturation degree is a ratio between the actual aluminum, the actual solubility product against the equilibrium solubility product. And then the right side figure shows the relationship between the oxygen content and the supersaturation degree, which is necessary for the inclusion nucleation. You can see that when the oxygen content is quite low, you need a very high supersaturation degree to achieve the nucleation of inclusions. This is understood as the influence of interfacial tension between molten steel and oxide, because the oxygen is a surface active element, and then it will dramatically decrease the interfacial tension. So it's explained in this equation. Here is the relation between the oxygen content and the interfacial energy like this. So both of the oxygen or sulfur are the very major surface active elements. So you need to be carefully evaluate those influences on the nucleation of inclusions in terms of the kinetics. The last one is the growth mechanism of inclusions. Major three ways considered. First one is a collision and coalescence. So when you put the deoxidizers in molten steel, it's strongly agitated within, and then very tiny oxide inclusions, for example, are formed. And then, because of the continuous agitation of molten steel, actually the collision of inclusions may happen. And then the sintering and coalescence happen simultaneously, and inclusions become larger and larger like this. The second one is the diffusion of constituent elements. This is quite easy to understand. So dissolved oxygen and dissolved deoxidized come together to form some compound on the surface of existing inclusions. And then this inclusion becomes larger. The last one is the Ostwald ripening, which is the influence of interfacial energy on the different solubility of oxides. So when you have the larger and smaller particles together, as you know, the Ostwald ripening will result in the further increase of the larger inclusions and then disappearance of the smaller inclusions like this. So the growth of inclusions is important to in molten steel because the buoyancy force of inclusions depends on the size of inclusions, and larger the inclusion is, easier to float up to the top of the molten steel to remove. So but finally, the very tiny inclusions may remain within the molten steel, and it solidifies together with molten steel. It remains in the steel products as a form of oxide inclusions. Okay, and then as I mentioned, the application of uh, complex deoxidation is like this. So here is one way to achieve the combined deoxidation. So as I mentioned, the promotion of coalescence of inclusions might be possible by making liquid inclusions. And then the levitation speed of inclusions may be improved. Or the formation of liquid oxide will decrease the liquidus temperature on one hand, and on the other hand, the activities of constituents are decreased as well. And then you can promote the deoxidation reaction. So the common major combined deoxidation is a combination of manganese and silicon to produce the manganese silicate, for example, or the use of calcium and silicon to form a calcium silicate, or the calcium aluminate, or the aluminum silicate, or something like that. So as you can see from this diagram, binary phase diagram between alumina and CaO, actually, if you put only alumina, only aluminum, the alumina is produced, and it's quite hard, and the melting temperature is quite high. But actually, by adding some calcium within the aluminum killed steel, you can modify the alumina into the calcium aluminate. So actually, the CaO is formed in the molten steel, and alumina pure Al2O3 is converted to the CaO Al2O3 liquid. And then this oxide inclusion is quite soft compared to the very hard alumina inclusions. And then even some portion of calcium aluminate remains in the steel product, you can easily break into the very tiny inclusion during the rolling or forging process. So you can convert this, the very harmful alumina inclusions to the harmless soft calcium aluminate inclusions. Thermodynamically, as well as mechanically, the inclusions can be converted. Okay, so time is almost coming. So I just rushing the final part. These here I put some figures to show the change. I can just take the one example. Change to show the change of oxygen refining limit and related technologies in Japan. This is almost 20 years ago, reported in some Japanese article. But anyway, some professors summarize this relation between the year before the World War II to the current stage to show the refining limit in terms of oxygen. So you can see that before World War II in 1940, the possible achievement of refining to reduce the oxygen concentration was in this range. But because of the continuous technical development, the defining limit is decreased, and then nowadays we can achieve to this level. Or nowadays it comes to the even less than 1 ppm. So but of course, in order to achieve this refining limits, there are many technical developments as shown here. And these technical developments are supported by the various demands from the society. So you can just understand why these technologies are required and why these very low oxygen concentrations were demanded from the society. And then this is the case for oxygen. I don't talk the very detail for nitrogen, carbon, and sulfur. But you can see the many demands, and then many processes were developed. I believe that those are mostly shown the situation in Japan, but you can understand this is just a worldwide trend. So in order to achieve the very low concentration, or in order to achieve the necessary impurity level, depending on the steel products, you need to choose the processes like this. So this is just an example. to show the Japanese situation. But anyway, if you want to produce the relatively low oxygen steel products, you need to use LF or RH or whatever, for example. So secondary steel making method are quite important to achieve such a high grade steel. And then this table shows the achievements or developments of many secondary steel making processes after the World War II. We can categorize these things with several things. First one is the vacuum degassing method. Uh, Very old one was the DEHA, DH, but soon after that, the RH process was also developed, and this is a common way nowadays to degas the molten steel. So in this case, the vacuum degasser uh, is introduced with two schnockers, and then using these two schnockers, the intake and outflow of molten steel is made. So actually the circulation of molten steel happens like this. And then the dimming actions or the degassing reactions for the hydrogen or nitrogen can be achieved within this tank degasser. Nowadays, the modern RH process is installed with many defining functions using the lances or using the fluxing machine, fluxing, fluxing equipment or something like this. Anyway, we have many modern RH processes, and this is still the quite common processes in the world. Ladle refining is also important. First function is alloying, or the second one is inclusion modification. And also the desulfurization can be achieved by this process. The last one is the refining, but with the arc heating process like this. So you can also tune the temperature by using the arc heating processes like this. The last one is the control of the non-metallic inclusion modification by calcium treatment, as I mentioned. The alumina inclusion is quite hard, but in order to change it into the calcium aluminate, we can utilize the calcium silicon metals, and then the calcium silicate is formed, calcium aluminate is formed. Okay, so this is just some examples I experience nowadays, but due to time limitation, I will skip those things. So you can read it later on. And if you have any question, just you can email me. I will try to answer your questions as much as possible. So I will skip these parts. So the concluding part, just I made two figures. Actually, the inclusion control can be achieved through the secondary refining, casting, and also the heating and processing part, post-casting process. So there are many functions in each process. In the secondary refining, we can normally control the primary inclusions. That's why we have intensively studied, not only me, but many previous researchers studied the deoxidation equilibria, reaction kinetics, as well as the fluid mechanics of these things. Within the casting process, the microstructure control, temperature change, or solid segregation, solid liquid interface, those many changes would influence the inclusion's properties quite significantly. In the heating, I mean the post-processing, you can see the microstructure and precipitation control can be done. So we still study these things intensively in order to control the inclusions precisely from the secondary refining part to the casting and heating process. So still the inclusion methodology is quite important part to achieve the very high grade clean steel production. And then we need to make the continuous effort for that one. So I believe it's almost time. So thank you very much for your time. And I would accept the questions if you have.
Okay, thank you, Professor Matsuura, for the nice talk, especially on say inclusion metallurgy, say casting, secondary refining. So you discuss a huge content, okay, within this say within 1 hour at least. So now I'm opening for say question and answer session. So if anyone have any question from the say audience, so please raise your hand. I can unmute you and then you can ask your question. Anyone have any question? Okay, so yeah, one question you have. So can you ask?
I have a question related with electroslag remelting. How electroslag remelting is it more effective than the other deoxidation processes?
Sorry, I didn't catch you.
The electroslag remelting process, is it more efficient than the other deoxidation processes?
No, I think it depends on the steel products you want to produce. The electroslag remelting process is, as you know, the molten steel is travels within the molten slag, right? And then during that process, some existing inclusions already in the starting materials can be absorbed by molten slag. But in other words, I would say that some elements might be entrapped again within the steel products, and then it may contaminates the molten steel again. So it depends on the steel grade, I think. But one important point is that you can modify the oxide inclusions, for example, or you can reduce the gas elements in the steel material. If you choose if you choose the proper slag composition.
Okay, there's one more question. How by changing the activity, we can change the morphology of the inclusions? What is the physical mechanism behind that?
Oh, I see. You're talking about this one?
Yes.
Yes. Actually, it depends on the firstly, when you see the activity of oxygen is quite high, which means that roughly I would say that the oxygen concentration around this inclusion is high. So in that case, as I mentioned, since the oxygen is surface active element, actually the most of oxygen is accumulating on the interface between this oxide and molten steel. And then interfacial tension is quite low. And then I believe in that case, the oxide inclusion can grow. The nucleate from many points of the interface between the molten steel and the inclusions. On the other hand, when the metal activity is quite high, oxygen content is very low. So it means that the growth of this non-metallic inclusions is governed by the transport of oxygen in molten steel. That's why the facetic I mean the growth of inclusion is happened. So meantime, when the oxygen and metal activity is in the middle range, I think this I would say that this may form the dendritic structure of inclusions. So I can say that both the I mean the not segregation, but the transport of metal element and oxygen element may affect to form this dendritic form, in my understanding.
Okay, that was quite nice explanation. Then I have one more small question. For the inclusion growth, how Oswald ripening is different than the collision and coalescence mechanism?
Oh, I see. I didn't describe the very detail about Oswald ripening, but actually the Oswald ripening happens due to the different solubility of these two particles in the molten metal. Okay, this is just an situation that you have two oxide inclusions. So if this is alumina, both are alumina, okay? So the material is the same, but the size is different. In that case, the because of the different curvature of this, I mean the particle, the solubility of this smaller particle is larger. And then once these small particles slightly dissolve to this molten metal, those dissolved elements are transferred and then consumed to the formation, I mean the growth of these larger particles. So such a kind of thing happens continuously, and then finally the smaller particles completely dissolve in the molten steel and disappears, while this larger particles actually absorbs these smaller particles to become bigger. Okay, this is a mechanism of Oswald ripening. Compared to this, the collision and coalescence is just a collision of, I mean, the particles. That is just a physical contact between two particles.
Okay, thank you.
Sure.
Okay, so thank you. Anyone have any question? Or we can conclude this session. Okay, so no one have any question right now. So thank you, Professor Matsuura, for accepting the invitation and for your valuable time. So thank you very much.
Thank you very much.
Yeah.
Have a nice time.
Yeah. Have a nice time to you also.
Thank you. See you.